In this video, we'll practice calculating probability and odds using tables of counts. Throughout, we'll work with the climbing dataset, which includes information about a sample of mountain climbers. Each row in the dataset represents an individual climber. For example, row 1 represents a climber that attempted to summit Mount Nampa, but did not use oxygen and was not successful. Using this dataset, we can explore both the success and failure among the climbers, as well as their oxygen use. To this end, a table of counts can provide some insights. The table here counts up the number of climbers by success or failure, and oxygen or no oxygen use. A natural question here is, what's the probability that a climber is successful, which we can denote as P success, as shown up here. To answer this question, we need to know, first, how many total climbers there are, and second, how many of these climbers were successful. To begin, we can obtain the total number of climbers from the column of counts n. Adding up the number of climbers that fall into each success and oxygen group, there are 2,076 total climbers. Among these climbers, the two bottom rows represent climbers that were successful. In total, there were 807 successful climbers, 309 of whom did not use oxygen, and 498 that did. Putting this together, then, we can calculate the probability of success by the ratio of the number of successes relative to the total number of climbers. That is, we want to know how many successes out of how many total climbs there were. Plugging in the counts from the previous slides, the probability of success is thus 0.39. That is, 39% of our climbers were successful. This type of probability has a special name. It's a marginal probability. In general, this just means that we're calculating the overall probability of success. That is, overall 2,076 climbers. Further, we can re-express the uncertainty of climbing success as odds by dividing the probability of success by 1 minus the probability of success, the result being 0.64. That is, the probability of climbing success is only 64% as high as the probability of failure. Consider a second question of interest. What's the probability that a climber is successful if they use oxygen? That is, instead of exploring success among all climbers, we want to narrow in on success among oxygen users. This probability is represented by the notation here. We want to know the probability of success if a climber uses oxygen. Thus, we need two pieces of information here. How many climbers use oxygen, and how many of these climbers were successful? To the first question, 601 climbers used oxygen, combining the two counts highlighted here. And among these 601 climbers that use oxygen, 498 were successful. Putting these together, we can calculate the probability of success among oxygen users by the ratio of the number of successes among oxygen users relative to the number of climbers that use oxygen in the first place. Plugging in the counts from the previous slides, we get a probability of 0.83. There's an 83% chance of success if a climber uses oxygen. This type of probability also has a special name. It's a conditional probability and can be read as the probability of success given or conditioned on oxygen use. That is, it's the probability of success just among oxygen users, not overall climbers. Further, we can convert this conditional probability into odds. The result being, by plugging in the probability of success given oxygen over 1 minus that probability, we get an odds of 4.88. That is, if a climber uses oxygen, their probability of success is nearly 5 times their probability of failure. Stepping back, we've calculated both a marginal and conditional probability of success, and these tell us 2 different pieces of information. Overall, we can say that a climber has a 39% chance of success. But if they use oxygen, their chance of success jumps to 83%. Let's practice these concepts, now focusing on oxygen use instead of success. First, what's the overall probability that a climber uses oxygen? I encourage you to pause your video and try calculating this on your own. To calculate this marginal probability, we want to compare the number of oxygen users to the overall number of climbers. Again, there were 2,076 total climbers in the data. And among these, 601 used oxygen, combining those that were successful and those that weren't. Plugging in these 2 counts, 29% of our climbers used oxygen. That is, if I take a climber at random, the probability that they used oxygen was 29%. So how, if at all, does this figure change if we know that a climber was successful? That is, what's the conditional probability that a climber used oxygen if we knew they were successful? Again, I encourage you to pause your video and try this calculation on your own. To calculate this conditional probability, we need to narrow in on just the successful climbers, the denominator here, and how many of these successful climbers used oxygen, the numerator. Looking to our table, there were 807 successful climbers in our data set. And among these, 498 used oxygen. Then plugging these counts into our formula, the conditional probability of oxygen use given a climber was successful is 0.62. Let's compare and contrast the marginal and conditional probability of oxygen. First, overall, there's a 29% chance that a climber used oxygen. But if we know that they were successful, the chance that they used oxygen jumps to 62%. In general, this example again illustrates that marginal and conditional probabilities may differ. And conditional probabilities can also differ. Though the conditional probability of oxygen use given success is 0.62, remember that the conditional probability of success given oxygen use is 0.83. Mainly in the first probability, the use of oxygen is unknown, but success is assumed or given. And in the second probability, success is unknown, but oxygen use is assumed or given. In general, the conditional probability of some event A happening given another event B happened is different than the conditional probability of B happening given the information that A happened. Consider a common example. Which conditional probability do you think is bigger? The probability that somebody becomes an NBA or professional basketball star if we know that they practiced a lot, or the probability that somebody practices a lot if we know that they're an NBA star? Well, the chances of becoming an NBA star are very low, even if you practice a lot. That is, the first conditional probability is roughly 0. In contrast, we can be pretty certain with a probability near 1 that somebody practiced a lot if we know that they became an NBA star.